Okay. Thank you very much. Okay, well, thanks to everyone in the audience for being here bright and early this morning. I think CME 302 has gotten earlier since I took it.
Yeah, it was to avoid conflicts with, some minor classes like CS229.
Oh, I see. Makes sense. Well, it's nice to meet you all. My name is David. As Eric said, I'm a recent graduate of the ICME. I just defended 3 weeks ago on this very day, actually. As I was sitting in, not these same chairs, but I was taking this same course 6 years back in 2019. And I'm here today to tell you a little bit about floating point programming, how to use it well. And in fact, we'll spend about half an hour, this first part of the lecture, going over a recap of the floating point fundamentals that hopefully you've seen, I believe, in Monday's lecture. Then I want to talk a little bit about some practical advice for how to quantify numerical precision, right? How to say, given this problem, how much precision do I need to solve it, and how to fix some common precision problems that will often occur in floating point programs. Then we'll take a 5-minute break. I've hopefully scheduled in enough time for lots of questions and interactivity. But to be honest, I wrote this lecture like last night, and I haven't timed it yet, so hopefully we'll have time for a 5-minute break. And then after that, I'll tell you a little bit about my own research about the stuff I was telling Eric about at my defense a few weeks ago, about how to do arithmetic effectively beyond machine precision, and in fact how to use computer automatic theorem provers to verify some of these properties that are really difficult to check by manual computation. But before we get all the way down there, first, I want to go all the way back to the genesis of floating point numbers, right? How did we get ourselves into this topic? And like I said, please let me know if anything here looks unfamiliar or if you haven't seen it before. But hopefully you've already seen that we come to floating point numbers from the simple proposition that we want to store real numbers on a computer, right? Because real numbers are so useful for modeling phenomena in the physical world. But we immediately run into a very big problem, which is that the set of real numbers is infinite. In fact, it's uncountably infinite, and there's no way we can encode infinitely many possibilities into our finite digital computers that we have here, right? So what do? Well, we do something that applied mathematicians love to do, and in some sense, I say, is the very core discipline of the subject, which is we make a deal with the devil, all right? We make this fundamental trade-off, and we say, okay, we are not going to attempt to store all of the real numbers in our computer. We are going to content ourselves with some finite subset f of the real numbers. We're going to descend down from the heavenly purity of the exact mathematical real numbers, right, which are beautiful in their rigidity, but are inaccessible to our, earthly machines that we have here. And instead, we're going to dive into this world. Yeah. We're going to dive into this world that's a bit messier, that doesn't satisfy the same rules, but that is tractable for our computers to use, right? We are going to give up a little bit of purity, a little bit of that absolute correctness for the power to actually do things, in the real world and do things on computers. And this game of trading off mathematical purity for mathematical power is something that really sits, I think, at the core of applied mathematics. And I think of quite a lot of things we do as making skillful deals with the devil. But that analogy aside, once we've decided that we want to do this, how do we actually pick this finite subset f, right? And there are several natural choices that you could think about. One of the most natural is you could say, okay, let's just take a uniform grid, right? I'm going to pick some grid spacing h, Maybe the grid spacing is 1, in which case we get the integers. Maybe it's 0.01, in which case what we call fixed point numbers. But whatever the grid spacing is, the technique looks basically the same. You're pretty much just doing arithmetic with multiples of that fixed step size h. And this gives you a number system that has constant absolute precision, right? Every number you can represent to plus or minus h over 2 in this system, as long as you're within range. But of course, constant absolute precision isn't really great for us as scientific programmers because nature comes to us at so many different natural scales, right? You may have in some problem some, astronomically sized numbers, 10 to the 10, 10 to the 20, and some microscopically sized numbers, 10 to the minus 10, 10 to the minus 20. And it's nice to have a system that can represent both of those things potentially within the same computation. So what we do instead is a trick called floating point representation, where we don't just take a single grid, but we instead take a nested system of grids, right? We have a different grid at each order of magnitude, and as we scale up, the spacing of that grid dynamically changes to give us constant relative precision rather than constant absolute precision. Is this making sense? This sounds familiar to everybody. Okay, very good. Now, I just want to point out that these are not the only two choices that you have. You could have other systems. For example, there's logarithmic representation. There's something newer called posit representation, which is being investigated now. But for the majority of use cases, fixed point and floating point, and indeed floating point especially, turn out to be the most common systems in use in practice today, for some good reason. Now, if we look at the actual anatomy of a floating point number, okay, an actual floating point number has a few parts that you need to be aware of. Basically, a floating point number is a little slip of paper where you can write down some digits, a plus or minus sign, and then a second block of digits. This plus or minus sign obviously tells you if the number is positive or negative. Then the digits here are called the mantissa, or sometimes called the significand of the number. They tell you the actual value of the number. And the length of the mantissa is called the precision of the number. So here I'm talking about decimal floating point numbers with precision 7, because there are 7 digits here. Then, of course, we have the base, which in this case is 10, and the exponent, which is 27, which tells you how big the number is, what scale it sits at. Or in other words, which one of those nested grids this particular number sits in, right? Now, you may already know that computers don't use floating point numbers in base 10, which we would call scientific notation. They instead work in base 2. So the only allowed digits are 1 and 0 in both the exponent and the mantissa, but essentially the same information is being encoded. Now, most of the digital computers that exist today, in fact, just about all of them, with very few exceptions, they natively support 2 different floating point formats, which are 2 different choices of how long the mantissa and the exponent can be. There's what we call the binary 32 format, or the single precision format, which is like the name implies, a 32-bit format with precision p equals 24. And there is the binary 64, or double precision format, which is a 64-bit format with precision p equals 53. Of course, these things are not, dictated to us by the universe. You could, in principle, pick whatever split you want between the exponent and the mantissa, but these standard splits were chosen, I think, back in the 1980s. I think IEEE standardized this in the 1985. And these standard splits have turned out to be a pretty good compromise for most applications, so we've pretty well stuck with them. There are other floating point formats, I should say. So many newer CPUs and GPUs will also natively support half precision, which is becoming popular for machine learning applications. But no processors I know natively support quad precision or above. Generally, double precision is the highest you'll find supported natively in your hardware. We'll get back to that point later, but that native hardware support is an important point.
So I think the old craze work one.
Oh, really?
Yeah.
Oh, interesting. And they could do, an operation in one cycle?
Yeah. They had support for quad, yeah.
Wow, remarkable. Huh.
But it was dropped.
Yeah, we've lost this ability somehow. Okay. At this point, I want to just give one quick aside. This is not quite recap, but people often ask, why do we use base 2 for floating point rather than base 10? Because, of course, you and I are all familiar with base 10 arithmetic. It looks nicer to us in many ways. For example, you'll often see people complain, oh, my computer can't store the number 0.3. Why is it so stupid? Why can't it represent such a simple number? And that's, of course, because it's using base 2, not base 10. And so some things that look like simple terminating fractions to us are actually infinitely repeating numbers as far as the computer is concerned. And there's an obvious reason, which is that computers prefer base 2 because a digital circuit is naturally a binary system, right? It's got zeros and ones inside of it. But actually, there's also a purely mathematical reason. If we put away the practicality, right, and we assume it's equally easy to make a base 10 computer and a base 2 computer, why would we prefer base 2? It's because of this issue that floating point is made out of nested grids, right? So if you imagine a system where you have base 10 nested grids, every time you hit a power of 10, the grid spacing becomes 10 times coarser, right? And then once you hit the next power of 10, it becomes 10 times coarser yet again. Whereas with powers of 2, the fall off is a bit more gradual, right? You're falling off by powers of 2 rather than powers of 10, and they're happening more frequently. So if you were to think about the sort of effective precision with which you can store each number, right? Every time the grid falls off, the effective precision goes down, it creeps back up, and then it goes down again. You get a graph that looks something like this, where you go down, then you go up again, then you go down, then you go up again, then you go down, then you go up again for base b equals 10. But for base 2, you get a graph that looks a little bit different, where you go down, then up again, down, then up again, down, then up again. it happens at a more frequent pace, but on average, the effective precision with which you can store a number stays higher than in base 10. And indeed, to make this formal, one can say that, okay, if you have a fixed budget of k mantissa bits, right? You've got k bits, you can decide whether you want them to be base 2 or base 10. Base 2 actually maximizes this expected accuracy, which is the negative log of the spacing relative to the number. Now, this is a relatively straightforward calculus exercise. If anyone's interested in the details, I can show you why this is the case. But the important part is that you can see that this has negative dependence on the base b. You would like the base b to be as small as possible, so you actually want to use binary floating point. It's more accurate in many cases than decimal. So okay, we're using binary floating point. This is the system that we're using. But it's not enough to just store the numbers in our computer, right? We want to actually do something. We want to compute with them. We want to do arithmetic. We want to add, subtract, multiply, and divide. But here again, we run into a big problem, which is that if you take any finite subset of the real numbers, no finite subset is closed under addition, subtraction, multiplication, division. There are no finite subfields of the real numbers R. Technically, this is a math class, so to be absolutely correct, I should say there is one finite subring, which is the set containing only 0, but you know, if you're content with a computer that contains only 0, well, you didn't need to do any of this in the first place. So we have this big problem, right? How are we going to construct a system that allows us to do arithmetic without leaving our set F? Here again, we have to make a second deal with the devil, okay? We have to say, all right, I'm not going to ask you for exact, real, honest-to-goodness addition, subtraction, multiplication, division. I will settle for having approximate operations. And these approximate operations are going to differ from the real ones in these three ways. So have rounding, overflow, and underflow.
I just want to ask a question to the audience. So, for example, he said the finite subset is closed under addition, subtraction, multiplication. So we saw that, for example, yeah, when you take two floating point numbers, as we explained, you know, you add them, there's some error and so on. But for example, if you take integers, okay, you add integers and so on, there's no problem, right? This is exact, there's no rounding error. With integers, you're fine. So, but then David claims that still this would not work. So what's wrong with integers, for example? It seems that integers you can do calculations exactly. It's closed. So what's the catch?
They're bounded.
Right.
Subset.
Exactly. So the problem is you're bounded, right? You have to store a bound number. So if you take the biggest one, you want to add 1.
Indeed. So you've got to deal with some kind of flaw in the arithmetic like this. And so the pact we make here is we say we're going to ask for these real, true mathematical operations, which I denote with plus, minus, times, and divide. We're going to settle for these rounded operations, which I denote by putting them in a round. This like rounded fake plus, minus, times, and divide. Now these are not too fake, okay? Let's recall how rounding actually works. So to compute, for example, the rounded sum of a and b, what we do is we first take those two numbers, a and b, and we calculate the exact value of the sum, as if we had infinite precision available to us, right? And then we see, where does that number land on the floating point number line, okay? If that number lands exactly on one of our floating point numbers, well, then the answer is obvious. We just return this floating point number, right? But in general, we will not get a floating point number. In general, we will get something that sits between two of these grid-marked points, in which case what we do is we look at that point, we see which of its two neighbors is closer, and we return the closer of the two neighbors. Now, in the case where you land exactly in the middle between two of these numbers, we use what's called a tie-breaking rule, which is rounding to even. What that means is, look at the mantissa of each of these numbers in the grid. I want to prefer the one that has an even final digit, right? So I prefer 1.10 over 1.01 here. This may differ from the rounding rule that you were taught in school. I was taught in elementary school that 0.5 always rounds up to 1. But actually, people prefer always rounding up, because it turns out that in the course of a very long calculation, that rounding up produces this bias that causes numbers to drift upwards over time. I believe this was first noticed by bankers in the 1700s, that their financial transactions would come out wrong after many, many roundings. So they devised a system called bankers rounding, which is to round to even. That way you round up as much as you round down. And that's what our computers do. And finally, in the event that you land outside of this number line, right, you land on a number that's too big, or if you land on a number that's too close to 0, what happens is you overflow or underflow. In this case, you return a special number, which is called infinity. It doesn't represent any real value. It's just a signal to tell you, hey, you computed something that's too big. Down here, if you're too close to 0, closer than any representable number, you just become 0, right? So underflow is this phenomenon that a technically non-zero result can become 0 as a result of rounding. Now, I want to make something perfectly clear. People often have a misconception that floating point rounding errors are somehow random or non-deterministic. This is not the case. This whole procedure is completely mathematically well-defined. It is deterministic, right? If you add the same two numbers today, tomorrow, yesterday, on Earth, on Mars, as long as you follow this procedure, you will get the same answer, right? So if you observe non-determinism in your floating point program, it's not because you're using floating point. That has nothing to do with it. The non-determinism must be coming from somewhere else, like you're using some, unsafe library that has a race condition or something like that. Rounding itself is completely deterministic. But we often model rounding as if it is introducing random numbers into our calculation because it's very difficult to predict ahead of time whether any particular rounding will go up or down, right? If I tell you, hey, I want you to multiply 3.74 times 2.96, you can't just, in your head see immediately which way that's going to round, right? So as a modeling choice to make things easier on ourselves, we will often think of floating point numbers as if they have these random errors, but indeed they do not, okay? And later, in the second part of the talk, we'll see how that non-randomness can actually be exploited to compute more precisely than machine precision. The second point I want to make is that this is a pretty involved process, actually, right? This idea that you calculate the exact value, then you see where it lands in the number line, then you round it. And so the miraculous thing is that your computer contains circuits that do this entire thing in one elementary operation, right? One single cycle of your computer's clock. That's actually pretty remarkable. And we'll see later just how difficult determining the rounding direction can be. But I just want to put a pin in that for now. It's kind of cool your computer can do all this in just one single cycle. It's all done in hardware. Okay, so rounding, as you know, is nice because it allows us to stay inside f, but also it breaks many of the algebraic properties of real arithmetic that you know from school. For example, addition is no longer associative. Consider an expression like this. Say we're working in 3-digit precision, and we add 0.01 plus 100. The answer will be 100.01, but because I only have 3 digits, that rounds down to 100. If I subtract 100, that gives me 0, right? It's as if the 0.01 didn't matter at all, because the rounding killed it in this operation. In contrast, if I had added 100 minus 100 first, that would give me 0, and then adding in the 0.01, I'd get a result of 0.01. So in this case, the 0.01 was annihilated. In this case, the 0.01 was not. Oh, I apologize. I should have used circled operators here. I forgot my own convention. But you see that's what's going on here. And in general, every time you do a rounded operation, what happens is rounding introduces a relative error bounded by the machine epsilon. So the machine epsilon is this number. It's 2 to the minus p, where p is the precision of the format. And the way to think about it is every time you compute a floating point sum, right, a circle plus b, what you get out is a number that's very close to a plus b, except for a factor of 1 plus delta, where delta is bounded in magnitude by the machine epsilon. And the same in this case as well. You're going to get, the product, something very close to it with this extra factor of 1 plus delta here. And delta is the machine epsilon. And so you can imagine when you write down some complicated mathematical expression inside a program, right, all these deltas will start combining, right? They'll like cascade through the program, and all the deltas will stack up. And these deltas can stack up in very unexpected ways, right? Because of this phenomenon where addition and subtraction work with absolute error, but multiplication and division work with relative error, you get these problems where a small absolute error can be a huge relative error. I think you've probably seen this example. I believe it's in Eric's notes. That if I have a tiny uncertainty in this number and a tiny uncertainty in this number, if I subtract them and they're very nearby, what I get out is a number with a huge relative uncertainty, even though the absolute uncertainty is basically the same, right? This is the phenomenon of destructive cancellation, which I believe you've seen before. Okay, so that's it for the recap. Hopefully all of that made sense. Are there any questions from the audience? Okay. Seeing none, we'll move on. So now I want to ask this question: how much precision do I need to do some computational task, right? I want to solve some linear system, I want to solve some differential equation, maybe I want to compute an eigenvalue. How much precision do I need? And unfortunately, there is no universal one-size-fits-all answer to this question. It depends on quite a lot of things. And indeed, the difficulty of this question is why we have this very rich field of numerical analysis, spanning, hundreds of textbooks and thousands of papers. Because it turns out every different type of question requires a different approach to understanding this problem of how much precision do we need. But I can tell you definitely there's some relevant factors you want to consider, right? So for one thing, you should consider, for what purpose am I computing this solution, right? If I'm, say, programming a video game and I want to find the trajectory of like a cannonball or something like that, that's a very different situation than if I'm doing a scientific simulation and I need really rigorous guarantees on the answer. If you're doing something like a video game or graphics, it merely has to look right to the human eye, which is a much less stringent condition, than being mathematically correct. So that's one thing. But provided that you are doing science, as I presume most of you are, the next question is, how fine are the gradations I need to distinguish, right? If you're doing something like computational chemistry, where you have to say, okay, which one of these is the more tightly bound structure, and you have to compare these really fine differences that start in like the 7th decimal place, well, that's going to call inherently for a lot more precision. But if you're doing, let's say, maybe a hypothesis test, right, where I just want to say, is, p less than 0.05, and I just want to differentiate this distribution over here from this distribution over here, you can probably get away with a lot less precision in the final answer, just provided that the numerical epsilons don't mix those two distributions, right? You also want to ask, how precisely do I know the input data? Because indeed, if I'm working on some problem with real-world data, and I only know that real-world data to 2 decimal places, I'll probably never be able to get a final answer to, much higher than the initial precision of my data. So very often it's not a computation problem, it's going back and getting better data. So you don't have garbage in, garbage out. And finally, does the type of problem I'm working on require higher internal precision than the desired precision of the final answer? There are some mathematical problems that have this property. Even if I only want the final answer to 3 digits, say, I'll have to carry all the internal calculations to 6 or 7 or 8 digits, something like that. Let me try to give you an intuition for why this occurs. So here's a nice example. Here's a problem that we solve all the time in applied mathematics. It is not the subject of this course, but it is one that the ICME students will be taking later this year. Suppose that you're trying to find the maximum of a function, right? You're trying to optimize a function. So I have this nicely, nice smooth function written down here, and I've marked the maximum right up here, that x star. Okay. In this view, it's very plain to see where the maximum is. But remember, the computer is not working with these smooth, continuous real numbers. It is working with a discrete representation of this function, right? So in the world of the computer, the function actually looks like this. It's their stair-stepping thing. And what you can see is that actually that optimal point has flattened out into this optimal mesa, right? All of these points now, in the eyes of the optimization algorithm, are equally optimal. You can't distinguish any one from the other looking at this representation. And so, while, of course, the effect is highly exaggerated here, the same thing happens no matter how high you turn up the precision. You can actually prove, I won't go through the proof, but it's a straightforward exercise in calculus, to say, look, if I want to locate if I can evaluate the function f to an accuracy of epsilon, I can only locate the maximizer or minimizer x star to an accuracy of square root of epsilon. And so what it means is if I want to find the maximizer to precision p, I must be able to compute the function with precision at least 2p. Right? There's this multiplicative factor on the internal precision that you need. And in fact, that's assuming that f itself has no internal loss of precision. Right? In practice, this will be worse. And this is, the first nice instance, something that we can call the condition number of a numerical problem. So the condition number is a really useful rule of thumb that will help us to analyze situations like this. Eric, I'm not sure if the condition number has been introduced yet at this point in the course.
It has.
Okay, excellent.
It has mostly for solving x equal b.
I see.
So, yeah.
Gotcha.
So, yeah, maybe you can explain in this context.
Yeah, okay. Well, I actually don't have the exact definition written up in my slides here, but I just want to point out that the condition number of a problem basically quantifies its sensitivity to small perturbations in the input. It's essentially like measuring a derivative of your problem, right, or at least a norm of a derivative. The technical definition relates something called forward error to backward error, which I believe is in the course text. Yes, so see that if you want the full gory details. But you actually don't need to know that to be an effective user of the condition number of a problem, right? So basically the condition number is this measure of sensitivity, right? If a condition number, for example, is 10 to the 5 of a particular problem, that means that a small perturbation in the input can be blown up by a factor of up to 10 to the 5 in the output. So if, for example, you're solving some problem and you want to have the final answer correct to 3 decimal places, right? And you compute the condition number of the problem and you find it's 10 to the 5, that means your internal calculations had better be carried to at least 8-digit precision, right? This is not a completely rigorous description. Of course, within a particular algorithm, the way that the epsilons and deltas stack up will differ depending on the specific algorithm you use. But as a general rule of thumb, this tells you how much precision you will need, assuming you're using a well-designed, backward stable algorithm. Now, how do you actually compute the condition number? Well, unfortunately, it depends for each type of problem how exactly the condition number is computed. But for example, as you see for solving ax equals b, the condition number of inverting a to solve the linear system has norm of a, Euclidean norm, Euclidean operator norm, I should say, norm of a times norm of a inverse. And for a few different classes of problems, I can actually write down, in terms of the condition number, what this bound will be. So as we've seen, for function optimization, for max or min, you will need double the precision plus whatever precision loss is incurred inside f itself. If you're doing numerical calculus, so if you're doing, say, finite differencing to get the first or second derivative, or you're doing integration, in this case, you will need double the precision plus whatever precision loss occurs in f, and here you will need p plus what's called the condition number of the integral, which is basically how much cancellation occurs between the different regions of f. For
incidentally, the integral is the same as the summation formula.
Mm-hmm. Indeed, for solving a linear system, I've written in this form now in terms of the max and minimum singular value, but it's the same thing as before. And for computing eigenvalues, actually that's even different than solving a linear system. This has to do with how symmetric or not symmetric the matrix A is. So this value over here is you have to take a particular eigenvalue, look at the left eigenvector and the right eigenvector, which is, say, the eigenvector of A and A transpose. And if those are not pointing in the same direction, the problem gets worse and worse conditioned. And finally, for other problems like evaluating a transcendental function, say sine x, log x, whatever, this depends on the particular function, but typically you will need higher internal precision inside to get good precision outside. Right? So this gives you some idea of how for different numerical problems you have different behavior of the error stacking up.
So for eigenvalue, this was kind of very briefly explained, but in different words. For example, using normal matrices, then you have if for normal matrices, then the eigenvectors are orthogonal. Okay, so then this is perfect. But then when the matrix is far from normal, then you can have this case of eigenvectors that point in the same direction, very low condition, and then you get this new condition.
Okay. Any questions? Everything making sense so far? Oh, yeah, what's up?
So like the closer they are to eigenvectors pointing in the same direction, the closer to the singular value being equal to 0. Right?
Yeah. So if they point in the same direction, then the computation is more stable. And if they point in nearly orthogonal directions, the computation is very unstable. Which is basically saying if A is very similar to A transpose, right, they have very similar looking eigenvectors, then the problem becomes easier. But for a highly unsymmetric matrix where the eigenvectors of A and A transpose look nothing like each other, that's really hard. And that's the interpretation here. Oh yeah, the eigenvectors should be taken to be normalized. I mean, it's an arbitrary factor, but assume that they're both a unit norm. Yeah, what's up?
How is this required internal precision being determined, like in particular for the integral? Like if your function is singular,
Oh, yes.
right-hand side, there's no dependence on like the singularity.
Yes.
Exactly like the sum, right? Like if you start summing up a bunch of numbers and you're hoping to get to a very, very small number at the end, then, well, the absolute error might be okay, but the relative error, which is what this is, becomes completely huge. Right?
Yep.
Like this exponential we talked about, this is the equivalent, but replace the sum. So indeed, if the integral of f is nearly 0, but f is just some big function, like you, even for example, if you integrate, like just cosine x over, from 0 to 100 pi, I mean, you're not going to get 0.
Yeah, I should clarify that this bound I wrote down for a continuous function f that has no singularities in the domain AB. If you're using some special method to handle singularities, that will also have to be analyzed separately. Yeah. But yeah, this is just purely an analogy with the case of summing a list of numbers. Anything else? Okay. Seeing none, let's move on then. So, so here's a list of things that you can try to use to determine the precision you need to solve any given mathematical problem that's in front of you. There are, of course, many problems not on this list that I haven't talked about, and indeed, many problems we don't really know, actually, what the real error behavior of it is. Training a deep neural network, I think people are trying to work out, how little precision they can get away with and still have the models come out well. So, lots of active research going on here as well. But finally, to round out this first part of the talk, I just want to talk about how to avoid these problems caused by rounding, overflow, and underflow, right? The negative consequences of our deal with the devil here, when you see them in your own numerical applications, right? Give some concrete advice for how you can try to avoid these things. So I'll start with overflow and underflow, all right? We'll put rounding off for now. Because overflow and underflow are, one, they're pretty easy to diagnose in your program, right? If you start getting infinity or nan values, these non-numeric values out of your program, okay, there's an overflow or underflow going on. And thankfully, overflow and underflow are usually easy to avoid. They're usually not reflecting some essential feature of the problem. They're usually reflecting just some, programming choice, or, that could be corrected. And the reason that I say this is because I am not aware of any scientific or engineering application that actually uses the entire full range of double precision floating point, which is 10 to the minus 300 up to 10 to the 300, right? I can actually make this statement with quite a lot of confidence because the scale of the universe, it turns out, is only 10 to the 60. If you ask the question, what is the length of the entire universe according to our best current cosmological models, this is roughly, I believe, 10 to the 27 meters, the scale of the observable universe. And you can ask the question, what is the smallest possible length that quantum mechanics could possibly let you measure? This is called the Planck length.
It's actually only 10 to the 27?
Yeah, surprisingly.
Yeah, it's not that big.
Yeah. And if you, if you're running a foot race, it might be a while, but you can also ask the question, right, quantum mechanics says that there's finite resolution in the universe, essentially, right? There's a length past which you statistically cannot distinguish a particle being here from a particle being here. That length is the Planck length, and it's roughly 10 to the minus 35 meters. So if you look at the ratio of the biggest possible length to the smallest possible length, this whole thing is about 10 to the 62. So in any program, any length has got to be bounded by 10 to the 62, right? Unless you're telling me you're simulating something that fits outside of the universe, in which case, okay, maybe you need some more numbers than this. But for us who live inside the physical universe, this is all fine. Even if you say, oh, I need to measure this length cubed because I'm measuring volume and not length, 10 to the 180 still fits perfectly fine in this regime, okay? So if you are encountering, numerical overflow or underflow, it certainly does not represent something physically measurable in the universe, right? It is an artifact of how you have set up the calculation. And I'll just point out there's like one exception to this, which is if you're doing cryptography or computational number theory, some field where you study the numbers as objects in of themselves, rather than thinking of numbers as measurements of the universe, right? Those guys need truly huge numbers, okay? And in fact, floating point is not typically used there for other reasons of precision. But assuming you're not doing one of these two things, your numbers should fit well within double precision. So to avoid overflow and underflow, Well, one thing is that if you're working with really huge or really tiny numbers, and usually these come from either combinatorics, like you're multiplying together all the permutations of something, or probability, where you're multiplying together a bunch of really rare events, they're multiplying the probabilities of them. The simple answer here is just to take logarithms, right? So instead of trying to compute n factorial, compute log n factorial instead and restructure your calculation to work with that. Instead of calculating the likelihood directly, work with the log likelihood, as every statistics book will tell you to do. Even on paper, this makes things easier, let alone inside a computer. And whenever you have some formula that's producing really huge internal numbers, but you know the final answer can be reasonably sized, you can usually rewrite that formula to avoid the huge intermediate number. I'll give you an example. Suppose, for some reason, you need to compute the 50th root of 100 to the 50 plus 99 to the 50, okay? 100 to the 50, that's a huge number, okay? That actually, I don't think will even overflow a double, but suppose that it did, right? Suppose that this number were really huge and this is going to be a problem. Well, the thing is, you know, the 50th power will be canceled out by the 50th root, right? The final answer is not going to be that big. We just need to avoid that intermediate calculation. So here's what you can do, very simple. Just pull out that factor of 100, right? It's raised to power 50, then taken to the 50th root. You can just pull it out and rewrite this as 100 times 1 plus 0.99 to the 50, and 0.99 to the 50 is going to be a very reasonable number. Turns out that it's about 0.009. And doing the calculation this way, you'll get a very reasonable answer without the huge intermediate number. A very similar one. This one comes up in statistics sometimes. You have to compute what's called the log sum of exponentials. And here, again, e to the 2000 is going to just absolutely kill you, right? There's no way that's fitting inside double precision, but you also don't need to do that. Again, take the 2000, pull it out as a factor outside the log. What you get is 2000 plus log of 1 plus e to the minus 1. That's a very reasonable calculation, and it comes out just fine. So, in a situation where you're seeing really huge or really tiny numbers, you can usually do some algebraic trick like this, okay? Rewrite the calculation to make the intermediate numbers go away. Make sense? Okay, now let's get to the issue of rounding error, and this is a much trickier one, right? Rounding errors are sometimes just inherent to the nature of a problem, right? In that computational chemistry example I showed you earlier, you just need to compare these two really close numbers. There's no getting around that. But you can often take a mathematical expression and rewrite it to reduce or eliminate destructive cancellation. Here's a classical example, which is, suppose you're calculating the square root of x plus 1 minus the square root of x, okay? This, as we've seen, is a difference of two numbers that are quite close to each other if x is large, right? They'll share a lot of common digits, so it'll be hard to get a good accuracy out of the answer. But it turns out if you do some algebraic manipulation, if you multiply and divide by the conjugate root, if you remember what that is, then you'll see that this is equivalent, actually, to 1 over root of x plus 1. And this does not suffer from any destructive cancellation. In fact, these two have the same sign, so everything is fine on the right-hand side. Classic example here of rewriting a mathematical expression to make it more numerically stable.
Okay, as it turns out, there is a very similar equation in the exam.
Oh. Oh, no.
It's not that.
Okay.
But it could be a useful thing to consider.
Okay.
So are you changing the exam?
What's that?
So are you changing the exam?
No.
Okay. Well, everyone take note of that then.
It's not that, though, but
Okay. Okay, so yes, this is a very classic example. Another one that you probably know is actually the quadratic formula. If you need to solve an equation, ax squared plus bx plus c, it actually turns out that the standard quadratic formula is a really bad way to do it numerically. Let me make sure I'm not running out of time here. Yeah, I'll briefly go over this. Okay. Well, I got to save time for the second half here. So let me see. I'll do this over here. So if you remember the quadratic formula, right? It's negative b plus or minus the square root of b squared minus 4ac over 2a, right? And let's call the two roots r1 and r2 are given by this formula, right? So, of course, the problem is that r1 and r2 solve ax squared plus bx plus c equals 0. taking a look at this formula, there is something very similar going on to the previous one. If you suppose that b is quite large, right, then square root of b squared minus 4ac is very nearly b, and so here you're taking negative b plus b, a lot of destructive cancellation there, right? So there is a straightforward trick to fix this. When you take this plus and minus, one of these two signs will be good and the other one will be bad, right? One of the two signs will agree with b, the other will disagree with b. Let me take the one that agrees with b, so that would be minus the sine of b times this. I'll call that my R1. Then it turns out there is a very straightforward algebraic relationship between R1 and R2. Namely, if you take R1 and R2, the product, there's something called Vieta's formula, which tells you that the product of these equals negative, I think it's C over A, or is it A over C? Hang on. C over A, I believe. Oh, okay. Thank you. Wow, I'm forgetting all my competition math now. So, knowing this, if you have R1, you can easily work out R2 in a numerically stable way. Just move this to the other side. So if you need to calculate both roots of a quadratic, this is the way you should prefer to do it rather than directly using the quadratic formula for this exact reason. And finally, it's also possible to take some algorithms and rewrite their order of operations in order to improve numerical stability in a very similar way. One that I think you will either already see or see very soon is the Gram-Schmidt procedure for orthogonalizing a set of vectors. You may know that you shouldn't actually do Gram-Schmidt as is written in textbooks because it is somewhat numerically unstable. An error introduced early on will propagate through the entire calculation. You should instead prefer the modified Gram-Schmidt algorithm, which does the same operations, right? So it's not any more complicated than original Gram-Schmidt, but it reorders them in such a way that an error introduced up here will not propagate into all the subsequent vectors down here. And if you're doing statistics, there's a very similar thing where what's called the one-pass variance algorithm is quite bad. If you want to compute the variance of a set of numbers, you should prefer the two-pass variance algorithm. In this case, the two-pass algorithm is a little bit slower, but this one can give you a totally garbage answer. So it's worth taking the extra time to get yourself a good answer. And finally, in this issue of rounding errors, I just want to point out that there are some very interesting tools that will let you analyze programs to find problematic expressions. So there's this tool called Herbie that I believe is a joint effort between the University of Utah and the University of Washington. There's some very strong programming languages groups up there. What Herbie does, well, actually, let me just show you what Herbie does. Let me move this window down here, if it'll let me. Oh, geez. Hold on. Let me just do this instead. Oh. Okay, fine. So, Herbie is this tool, there we go, where you can enter some mathematical expression, like that problematic one we saw earlier, right? Root of x plus 1 minus root of x. And say, okay, I'm interested in calculating this for some bound of x, right? Say 1 to a billion, just for example, here. And what it will do is it will take my expression and then apply a bunch of known algebraic rules to it, like multiplying and dividing by the conjugate roots. And what it will try to do is find for me a more accurate way to rewrite this program. And you can see here it finds the exact one, 1 over root of x. For some reason it's written strangely, minus 1, but it's plus 1, x plus 1 over x. And you can see that this has much higher relative accuracy than my original program that I started with here. And so a tool like this is really helpful if you have some complicated formula in a numerical program that you're having problems with. And indeed, if you go back to the home page, you can actually see that they have a list of formulas that people have submitted. And you can see that in many cases, well, here's the classic case, you can get a pretty substantial improvement. So in here, a case like this, root of x plus 1 minus 1 is one of these expressions that's very problematic if the numbers x are very small, which you can see this person was interested in. But you can rewrite it this way and get a much better answer. So, oh, yes, it will indeed find polynomial rewritings as well, and it will also find optimal evaluation orders for polynomials. I'm not sure if there's an easy example on this page, but I have seen such things, yes. Okay, so that rounds out part one of today's lecture. Before we move on to my own research, are there any questions from the audience after seeing that tool? Yeah, what's up?
I like to give this program to some GitHub repository and we'll analyze
Oh,
operations.
good question. So there's some additional tooling needed there to like take the code in whatever language you've written in, right? Extract all the numerical expressions, rewrite them into the language of Herbie, and then check them. That tooling is not part of Herbie itself. You just provide Herbie with, the mathematical expression. So you need something that goes through your code line by line, rips out all the mathematical expressions and pastes them in. But people have done exactly what you describe and found errors in large code bases that turn out to be fixable. Yes, it's definitely something you can do. Anything else? Okay, if not, let's break for...
I have another question. So if you do have a code that does some calculation, is there some sort of automated tool to check for round-off errors? That sounds different.
Yes. So,
You run your code and somehow it's being checked.
yes. So there is this tool, so there are several tools that try to go along these lines to quantify rounding errors in a dynamic way. You've heard of something called, I think, Parsimonious is one of these. AMP for, I think, automated mixed precision is one of these systems. But these are, I think, unfortunately no longer maintained. I mean, they were research projects. I wrote one paper about them, and then that was that. But I know that there is this tool called, I think, Numerical Shaman, if I remember correctly. It is a funny name, but... Yes, this is the one. So Shaman is this project. It's this library that provides a type called S-double rather than double. And basically the idea is that an S-double tracks, I think, like the tree of expressions that was used to build it and evaluates the numerical accuracy of each operation in that tree using essentially automatic differentiation to measure the condition number of each operation. And then it will... Once you rewrite your program to use S-double instead of double, Shaman will run your program and say, oh, you have a really sensitive operation here where you need more precision. So systems like this do indeed exist. They are usually difficult to use. I mean, you can see here that changing your entire program to use S-double rather than double is a pretty invasive change and may lead to other things breaking. So if you want to use tools like this, it's better to use generic programming languages like C++ or Julia, right, where you have access to easy swappability of types. But yes, these systems are being worked on, but they're hampered by the fact that a lot of numerical code exists in non-generic form, and so it's not easy to just swap things out like this. Okay, perfect. All right, let's reconvene, everybody. So, like I said before, in the second part of today's lecture, I'll tell you a little bit about the research I've been doing in trying to do arithmetic beyond machine precision, and I want to make sure this class ends on time. So I'll try to go through this quickly, but of course still interrupt and ask questions if you have them. So we are currently in the age of what we call exascale computing, which means that our biggest computers and the biggest problems they can solve involve on the order of 10 to the 18 floating point operations, right? We now have individual computers, not individual ones, clusters, but, systems, single combined systems that can do a billion floating point operations per second. That's a truly staggering number to think about, right? And I just told you that those are double precision floating point operations on these machines, which give you a machine epsilon of 2 to the minus 53, which is roughly 10 to the minus 16. Now, if you look at these two numbers in the slide, you may get the feeling that something is wrong here. This is, of course, a mathematics course, so theorem, 18 is bigger than 16. All right? If for some reason you need a proof, it is because the difference is positive. All right? And what this means as a corollary is that actually 10 to the 18 is quite a lot bigger than 10 to the 16. So it's totally conceivable that once you've done 10 to the 18 floating point operations, you've introduced 10 to the 18 machine epsilons in there, you may have completely washed out the machine precision, right? So at the very extreme scales of what we can do today, double precision is coming up a little bit short of where we need it to be to get useful results out of these really, really large-scale simulations. And you don't have to take it from me that this is a problem, right? Here's a report. Oh, yes?
So you remember the summation formula? There was an NU term. That's what she's talking about. The N is 10 to the 18, the U is 10 to the 16. This is right there.
Yes, precisely. So here, for example, is this report from the ICERM, the equivalent of ICME at Brown, where they said, numerical round-off error are now so greatly magnified in these large-scale computational simulations that we're having a bit of a reproducibility crisis. It's really difficult now because just some invisible difference in how you write the program can cascade and give you a totally different answer, right? This is becoming a real problem. Here's David Bailey, winner of a Gordon Bell Prize, a real luminary in numerical computation, saying that, look, in the future, moving forward, we will need to employ variable and extended precision arithmetic assisted with software tools to identify numerical instabilities in our software. He says, in fact, this is the only practical solution for scientific computing moving forward. Here is our very own Michael Saunders, right, who wrote many of the textbook algorithms you will learn later in this course, saying that quad precision stands to revolutionize optimization solvers, just as double precision did long ago, and say we need to beg the chip makers, please implement quad precision in hardware, a call that has unfortunately fallen on deaf ears. And if, for some reason, that is not convincing to you yet, here's Will Kahan, all right, Turing Award winner, ACM fellow, and the author of the floating point standard himself. Here's Will Kahan saying, we messed up by making double precision the default in all of our programming languages. We should have done quadruple precision. It's the humane option because it's caused us so much pain and suffering using double in these really large-scale calculations, right? So clearly there is this problem that at the very large scales we are needing more precision, but unfortunately, as we've seen, all of the major hardware vendors today don't provide it. There's this universal agreement that basically it's like too expensive to tape out in terms of transistor budget and the power draw that would be required on the chips. Now, of course, you don't have to just rely on the hardware of your computer to do these operations. You could also implement floating point operations in software, right? That whole procedure that we saw of compute the exact result, see where it falls, round it off, that could be done in the source code of your program. And so indeed, there are many software libraries that attempt to do this task. But as we'll see, these libraries are all much slower, right? They're involving hundreds of operations where native machine precision would just involve one, and the performance hit you get from this is really severe. Just to give you an idea, let's take a look at the source code of the GMP library, the GNU Multi-Precision Library, one of the most widely used libraries for this task. Here is its floating point addition function, MPF add. And you can see some interesting features here if you're a C programmer like me. The very first of which is you see there's dynamic memory allocation happening right at the top of this function, which is kind of crazy, right? Imagine that every time you want to add two numbers, you have to ask the memory allocator to go walk the free list and find you a free memory block. That's a really, really bad situation. And moreover, you have all of this complicated branching logic, right? You have all this logic about, oh, if the two numbers mantisses, if they line up like this, or if they line up like this, or if they line up like this, you have to do different logic in all of these cases. And this is real bad because nowadays we're working on data parallel processors like vector CPUs and GPUs. Those really don't like branches. They want to be able to do many operations in parallel, all taking the same branch. So looking at this, you may get the idea that, extended precision this way is a big scam. We can't be doing it. Imagine, this is a crazy situation, right? But thankfully, there's a better way. Also, this slide is very tongue-in-cheek. These libraries, I should say, these are not, foolish libraries that have been written this way for no reason. Libraries like this have been optimized for the case where you're adding immensely large numbers with millions of digits, right? Numbers that are megabytes long. And for that use case, dynamic allocation is a perfectly reasonable cost to pay. But as we've seen in scientific calculation, we don't really need to go all the way to that length. Usually we just need to go a bit beyond machine precision. We need to go to quad or hex precision or something like that. And that demands a different approach than something like this. As we know, floating point is this really complicated procedure, right? If you look at the circuit diagram of a floating point adder, there's so much going on. And if you want to implement all this stuff in software, you need to recreate all of these abstractions. But why simulate this in software when you already have a hardware floating point unit that does all these operations for you, right? It does all this mantissa alignment, exponent comparison, it does rounding analysis. Why don't we just use that? Well, the problem is the one that you have in your computer is tied down to a double precision adder or double precision multiplier. You can't just rip out that part of the circuit and apply it to quad precision. Or can you? there is a sort of clever way to get around this and make use of that hardware that's already there. It's called a floating point expansion. The idea is you take some high precision number you want to store inside your computer. Oh, yeah, there we go. And what you do is you'll just break it down in terms of machine precision approximations, right? So given your C, let me round C to the nearest representable machine number, which I'll call RNE here. Then I look at the residual. What is the difference between C and the nearest representable machine number? I'll call that x1, right? So now I have this correction term that should be added on to interpret the final value. You keep going this way, and what you can do is you can multiply the native machine precision p, right? You can get a representation of this number that's good to precision 2p or 3p or 4p, something like that. And one very important thing to do when you do this is to maintain what we call a non-overlapping invariant, right? The idea is if the two components of your number are overlapping in the middle, then you are losing some precision in the overlap, right, that you could otherwise have. You want the numbers to be non-overlapping like this, so you actually get the promised 2p, 3p, or 4p, whatever it is. So, okay, once again, we can store the numbers that way, that's perfectly fine, but just storing them is uninteresting. We want to do arithmetic, right? How do I add two floating point expansions in this format? You may think it's easy. I'll just take the first term, add them, the second term, add them, the third term, add them, the fourth term, add them, but unfortunately, this is completely wrong. This is not how this game works at all. If you do it this way, you'll find that all these future terms are garbage. It's no better than machine precision. And of course, we have these two issues, rounding and non-overlapping, that we need to consider. Right? So rounding, when you compute that first term, x naught plus y naught, you're going to get rounding error in that operation, right? And you need to carry that rounding error into the remaining terms in order to get a meaningful sum out of them. Now, this seems very difficult because when the hardware takes in these two numbers and adds them, it just chops this off. You never get to see it, right? So how can you possibly figure out what that is and propagate it into the next term? Well, thankfully, there actually is this really ingenious way to calculate the rounded sum and the rounding error both in one go. It's called the two-sum algorithm, and it was discovered by Don Knuth and Ole Muller in the 1960s. It's been known for a surprisingly long time. And it does this miraculously without using a single branch. It just uses branch-free machine precision operations. Let me show you how it works. So what you do is you take those two numbers, right, the 93.7 and the 7.54 that we saw before. I'm going to do this in base 10 for simplicity of our understanding, but the same principle works just as well in base 2. So what you do is you first add the two numbers and you get the rounded result, right, that 101, which is missing that 0.24 rounding error that we have in there. What I'm going to do is I'm going to take that sum and compute what I call the effective value of A, okay? So that's the sum minus B. What I'm going to get is this 93.5. So what you see is that even though A is in truth 93.7, it only managed to contribute 93.5 worth of its value into that sum of 101. I do the same game for B, and you can see the effective value of B is 7.5 rather than 7.54. And here you see 7.5 plus 93.5 is exactly 101. Okay, so these two effective values add up in the correct way. Finally, what I do is I look at the error. So I take the difference between A and its effective value, B and its effective value, and what do you know? If I put those together, I get exactly that 0.24 that went missing in the first line. Isn't that miraculous? Even though the computer didn't tell me what the rounding error was, I could easily work it out just by doing a few more operations. So that's what two-sum looks like. So two-sum allows us to propagate these rounding errors down the chain to sum two floating point expansions. But it's still not quite that simple because in addition to propagating the errors down the chain, we also need to make sure that the result we get doesn't overlap, right? And the problem here is that when you add two numbers like this, the digits are going to move around, right? So here, for example, we overflowed the top digit. It goes from the tens place to the hundreds place, right? And so the mantissa shifted one place to the left. In the event of cancellation, what will happen is the mantissa will shift to the right because the common digits will disappear. And in the extreme case, if the two numbers are the same, well then what happens is the mantissa completely vanishes, there's nothing there. Now you have an empty slot that you need to move the next guy into in order to have a non-overlapping number, right? And so you see the problem, right? The thing is, when you apply these two-sum operations to clear the overlap, you're playing like this game of whack-a-mole. So let's imagine you have these two floating point expansions here. I'll just represent them as these rectangular blocks, but you should think of them as like being the mantissa digits in like place value. So let's say I take these first two, I sum them, I get a result like this. This next two, I sum them, I get a result like this. The next two, I sum them like this. The next two, I sum them like this. And now I see, okay, this is my final floating point expansion, but I see S0 and S1 they are overlapping right now. So I'll apply another two sum to them to make them non-overlap. But now that moved it over there, so now it overlaps S2. I need to clear that. Oh, shoot, I need to clear that now. Oh, shoot, when I did that, it actually overflowed the top bit of S2 double prime, so now I need to come over here and clear that one. And now it did it again and did it again. You see the problem, right? You're playing this game of like chasing down, squeezing out all these last little errors. And so if you're going to write an algorithm to do arithmetic on floating point expansions, your algorithm better handle all possible ways that the inputs and the intermediate results can overlap, right? They could overlap like this, or like this, or like this, or like this, or like this. There's this combinatorial explosion of different possibilities. And this is understandably very difficult to analyze, and so unfortunately, subtle mistakes are not uncommon in the analysis of algorithms like this. Even, in fact, in the simplest case of a length 2 expansion, there's a very storied history here. So the first person to propose this technique of floating point expansion is someone named, I think, Theodorus Decker, who wrote this paper in 1971, in which he proposed this algorithm called add2 for adding what he calls two double-length numbers, x, 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 and y, y, y. Somewhat confusing names, but the algorithm is very intelligible, and if I write it in the modern notation of two-sum, this is what it looks like. Looking at it this way, it's still a little bit difficult to see what is exactly going on, so let me instead rewrite it like this, in this graphical notation, where every two-sum is this vertical gate, I'm calling it, where it takes in two numbers and spits out two numbers. Notice here the order is important. The sum comes out on top, the error comes out on bottom. And whenever I do a normal floating point sum, where I don't keep track of the error, I'm just going to write it like this, where I write this box to designate that the error has been discarded, right? Two-sum is the same thing as just, well, the sum is just two-sum with the error discarded. So that makes sense. So you can see Decker's add2 algorithm has a structure that's like this staircase step pattern that reduces 4 inputs or down into 2 outputs. Looks very reasonable. Looks like a very intuitively reasonable algorithm for this problem until you realize it is actually completely wrong. It turns out that add2, these two discarded terms can be so important that they add up to more than the two output terms. You can get a relative error of greater than 100% out of this algorithm, which is obviously real bad if you're doing some kind of important computation. So this was realized, thankfully, and in about the year 2000, there was a team of folks over at Berkeley who realized that add2 was broken in this way and proposed an algorithm called DDAdd to try to fix that up. And what they did, again, it's kind of difficult to read in this notation, but I'll show it to you this way. What they did was they added these extra 2 gates at the end here to allow this error term to potentially affect the final result. And you may ask, okay, is that enough of a correction to get the correct behavior? Well, again, this is a weirdly long story. So in the original paper, they claimed that DDAdd has relative error 2 times the machine epsilon, right? So 2 times epsilon squared, I should say, since we're getting double the effective precision using a double length expansion. But in fact, it turned out that this claim was wrong. About 17 years later, some other folks refuted this claim and gave a counterexample, relative error 2.25 times epsilon squared. And they conjectured that this was the true upper bound, when in fact that was also wrong. Some other folks, and I independently, found an even better counterexample with relative error 3 epsilon squared. Now, I'm not trying in doing this to like dunk on the authors of this paper. I mean, going from 2 epsilon squared to 3 epsilon squared, it is bad, but it's not like a catastrophic error, right? It's not going to invalidate the results produced with this algorithm. But the point I want to make here is that, I mean, the folks that wrote this paper, these are like some of the world experts in numerical analysis, right? We have an ACM fellow here, we have a Gordon Bell Prize winner, we have a Turing Award winner among the author list, and even these guys can get it wrong. I'm not saying I'm smarter than them. These are the luminaries of our field. They've done amazing things, highly respectable. But even the world experts can make mistakes in floating point rounding analysis. It's just that tricky to get this subject right. So what I did in my PhD thesis is I introduced a way to analyze algorithms of this type using automatic theorem provers, this tool we have called SMT solvers now. And what I did is I said, okay, let's consider this general class of algorithm. I'm going to call it a floating point accumulation network, which is just my fancy name for a branch-free sequence of sum and two-sum operations. And two-sum has this nice property that because the x plus y exactly equals the sum plus the error, as you sweep across this diagram, the total value never changes except when we discard a term, right? So what do I want to do to verify that a floating point accumulation network is correct? Well, what it means is for any non-overlapping inputs, x0 and y0, or x0, x1, and y0, y1, I want all of the discarded terms to be very small. They better be on the order of epsilon squared, and I want the output terms to be non-overlapping, okay? How can I verify this? There are a few existing techniques. One of them is what I call projection from real arithmetic, which is to say, okay, let's consider this a continuous mathematical problem first, prove it in that domain, then show it is stable under small perturbations, and therefore also holds in the floating point domain. This technique cannot work for an algorithm like this because in exact arithmetic, two-sum is just a plus b and then 0, right? It never returns any error. So a statement like this is not stable under small perturbations. It's not something you can see working from the real number world. This is a unique phenomenon to the floating point domain. You must reason about it here. There is also a collection of solvers that do what I call bit blasting, which is they say, okay, let's consider this whole thing as not a floating point function, but a Boolean function. I'll write out what a floating point adder does as a great big Boolean formula, and then I'll just see, is there any satisfying assignment to these Boolean variables? I'll just solve the SAT problem. And this will work in principle, but it is extremely slow once you have these complicated algorithms. For verifying 16-bit algorithms, it takes hours, it takes days to do float 32, and for double precision, I have not been able to find any solver that can do it in like less than a week. I just actually don't even think it's possible with the exponential scaling of this problem. So what you need to do this is you need a technique that reasons about the general shape of a floating point number without getting bogged down in computing every last bit, right? These algorithms are branching through, oh, what is this bit, what is this bit, and they're testing all 2 to the n possibilities. We don't want to do that. We don't need to do that. So what I said is, okay, let's just consider a very rough representation of a floating point number where I will only consider the sign, exponent, and the leading and trailing zeros and ones in the mantissa of that number. So here's an example. This set of parameters corresponds to a bit pattern like this with these don't care bits in the middle, right? The whole point of the technique is I'm going to abstract away the details that don't matter and only just care about the general shape of the number, right? And these variables are enough to express this idea that one number is very small or that two numbers do not overlap each other, just as linear inequalities in terms of these variables. So what I then did is I proved this collection, I think Eric has mentioned this, of something like 400 lemmas now. At first I was doing them one by hand, but eventually I found a sort of automated way to discover them that basically say, hey, if you do a two-sum and the inputs look like this, the outputs have to look like this. Right? The idea is the solver initially knows nothing about the two-sum operation. It thinks that 1 plus 1 could equal 7, for all it knows. And I'm telling it a bunch of impossible situations. I'm saying, hey, if you see numbers that look like this, the output has to look like this. If you see numbers that look like this, the output has to look like this. And in this way, by sort of selectively telling it relevant facts about the kind of numbers that affect the correctness of floating point accumulation networks, and by individually proving each of these lemmas, checking them separately against an automatic theorem prover, you can get a completely rigorous way to rule out all of those counterexamples. And if you just set up this satisfiability problem and impose these constraints, which for the sake of time I will not get into, then you can get a completely automated and completely rigorous way to check the correctness of one of these algorithms. And in fact, if you look at how fast this is using this new technique compared to the existing SMT solvers, which are already taking hours for float 16 and days for float 32, you can see that this technique is, it's first of all many times faster, and it also doesn't get harder as the numbers get bigger because the precision p is treated just as a parameter, right? So in fact, one of these proofs has a for all over all values of the precision p inside of it. You only need to do it once, and it's proved for every single one. So, having this procedure in hand, what I then did is I said, okay, I can now do a computer search over the space of all possible FPANs to try to find more efficient algorithms. Basically, I just did this sort of random statistical search inspired by thermodynamics, and I actually managed to find some really good new algorithms for adding floating point expansions. So here is a new algorithm that does the same task as DDAD did, but has a better relative error, and it's also faster. It's faster because if you look, these two gates can be executed in parallel, and these two gates can be executed in parallel. So the depth of this algorithm is only 4 as opposed to 5 down here. And so this is just an overall win, right? It's more accurate, and it has lower depth. And indeed, I've also found what is, to my knowledge, the first provably correct FPAN for adding triple word numbers and quadruple word numbers. And it turns out using a similar technique, which is just by expanding both expansions and then using a similar 2-prod like 2-sum, but it does products. You can also do multiplication this way and discover algorithms like this, and it's absolute monstrosity, this one here. I can't explain to you why the algorithms look like this, but I know they are provably correct using this technique, and their relative errors have to be completely bounded. And it turns out...
You cannot prove it's the best, it's optimal, in terms of computational cost.
Yes, that's true. It could be that there is an even better one hiding somewhere in this space that I've not yet seen. And it turns out that once you have addition and multiplication, you can actually get division and square root in a very simple way using Newton's algorithm, but I don't have time to tell you about the details. So I will just say that these algorithms, once you implement them, turn out to be way faster than all of the existing multi-precision libraries. They give you these huge order of magnitude performance improvements, right? I mean, there's like a factor of 10, maybe a factor of 100, in fact, over some of these older libraries. And if you use them to solve numerical problems, you get way better answers than were previously possible. Yes?
So this is an example of an eigenvalue calculation that's very difficult. You can see how on the left is the exact, on the right is the numerical calculation. So we'll see that eigenvalues actually are difficult to calculate.
Yes, very much so, indeed. I mean, for this very asymmetric matrix, it's a very difficult problem. And you'll see that the performance profiles you get from using these high-precision algorithms let you solve this really well, and also for solving linear systems. You can even get situations where doing it in higher precision is strictly better than doing it in low precision, even though each iteration costs more. Each iteration is getting more useful work done, and so you totally win out in the end. Anyway, that concludes this part of the talk. We are at 10:21, so I have to officially dismiss you. But thank you very much again for listening, and I'll be happy to stick around for questions. Microphone too.